Okay, so let's do a common particle equation style question. So let's read the question. Muons and antimuons are unstable, with the decay process producing three particles. When an antimuon, denoted by that symbol, decays, one of these particles is an electron neutrino, which has that symbol. Complete the table below and use your answers to identify the missing particle X. So we have a table here, and we can see we need to deduce what particle X is using the conservation of electric charge on the left hand and right side, which have to match, and the conservation of lepton number on the left and right side, which have to match. Now, one more thing that you do have to keep in mind here. Let's just note the wording of the question, right? So in the wording of the question, it describes what the process is that leads to this equation, and the process is the decay of antimuons. So, in other words, what's basically happening here is no energy is being added here at the start. So, all we have at the start is the antimuon, which means by the end of this equation, we do have to make sure that conservation of electric charge and conservation of lepton number are upheld, right? And we have the correct numbers for each of those. But we also have to make sure that the mass on the right hand side is not more than the mass on the left hand side, right? So since the entire process is the decay of an antimuon, it does not have any energy added. So you can have energy at the end, right? So you can actually have the mass on the right hand side is less than the mass on the left hand side, but you cannot have the mass on the right hand side is more because there was no energy added at the start here that can cause more mass to happen. But you can have less mass because you can think of it as energy being released, right? Which does happen in a equation in the decay process, right? So let's do the question. Now all the particles here are leptons, right? So they'll have a lepton number, so we should keep note of that. If they were baryons, for example, they'll have a baryon number, and all of these numbers have to be conserved, right? So conservation of lepton number. We've got a antimuon. Now, if you have this symbol here, this symbol right here, you have this line on top right here. It means it's an antimuon, right? Contrary to a muon. So you have a muon, and then you have an antimuon. So what's the difference? Well, antimuons have the same mass. So if you have an anti anything, a line on top of anything that makes it the antiparticle, it will have the same mass, but everything else is switched. The sign is switched. So the lepton number in this case of a muon would be +1, right? Because it's a lepton. And an antimuon has a lepton number of -1. The electric charge of a muon ordinarily is -1, but an antimuon has the opposite electric charge of +1. Right? So that's the other rule that we have to keep note of here. So knowing that, let's fill out this table, and it's very, very simple. 0 and 0 plus x, the charge of x has to equal +1, so this will be +1. Okay, and +1 and -1, which is equal to 0, plus the lepton number of x has to equal to -1 on the left-hand side. So x will be -1. -1, just like that. Right? Okay, so what is particle X? Well, for this, we have to refer to our standard model, which is in the formula sheet. So we can use this here to try and identify what particle X is. So we know two things about particle X. We know it has an electric charge of +1, and we know it has a lepton number of -1. Now, every normal lepton has a lepton number of +1, right? It's only the anti-leptons that will have a negative in front, right? So we can immediately tell that this is probably an anti-lepton, right? And since everything here is a lepton, and we've deduced that its lepton number is -1, it's probably an anti-lepton, right? So if it's an anti-lepton, the normal version of that lepton will have the sign switched. The normal version will have a charge of -1 and a lepton number of +1. And then the anti-version has a lepton number of -1 and a charge of +1, which is what we see here. So let's try and see which antiparticle here will give us a charge of +1 and a lepton number of -1. Okay, so immediately we can focus our attention just to the leptons here. So just the leptons on this. We're just concerned with the leptons, and we know it can't be any of these because these have a charge of 0, right? And we need a charge of +1. Now, these three have a charge of -1. But keep in mind, we are looking for an antiparticle. So the antiparticle of each of these will have a charge of +1, right? And it will have a lepton number of -1. So we can actually see here, all of these have a -1 charge and a +1 lepton number. All three of these fit that description. And so all three of these, the antiparticle of all three of these, if we just add the line on top to all three of these, it will also fit the description of having +1 charge and -1 lepton number, which is, if you recall, it's what we need. +1 charge and -1 lepton number. So what's going on? All three of these fit out, or sorry, the antiparticle of all three of these fit our description. So which one is it? Well, that's when we think about our third rule, which is the conservation of mass. So as it was explained in the question, we know that no energy is added at the start, which means that you cannot have more mass on the right hand side. You can only have the same mass or less mass, right? Maybe some mass was lost as energy on the right hand side, but it was never added, so you cannot have more mass, right? So you definitely can't have an antimuon, right? Because we already have more mass than the antimuon. We have an electron neutrino here and an anti-electron neutrino, which both have their own mass. Which, if we add an antimuon to the right hand side, now clearly we have more mass than just one antimuon. So we can't have an antimuon. Okay, well, what about a tau? Well, we can see the tau, the mass of the tau, the mass of the tau right here, the mass of the tau, we can see it's actually greater than the mass of the muon, actually by a factor of 10 to the 3, right? It's much greater. So we can tell that's definitely not the tau, because the tau will have much more mass on the right hand side. So by process of elimination, the only thing that fits the description that has a mass that is less than the left hand side is the electron. And since we're worried about the antiparticle of the electron, it is the anti-electron, which is known, by the way, as a positron. Positron, right? So that's our answer here. Okay, so let's do the second part of the question. Muons created in the upper atmosphere, approximately 10 kilometers above the Earth's surface, are secondary products from highly energetic cosmic ray interactions with nuclei of atmospheric particles. In their own frame, muons have a mean lifetime of 2.2 times 10 to the negative 6, with some lasting up to 3 times 10 to the negative 6 seconds. The speed of muons from cosmic rays entering the Earth's atmosphere moving in the direction of the observer on Earth is in the range 2.96 times 10 to the 8 to 2.997 times 10 to the 8 meters per second. Ignore the effect of the Earth's magnetic field on muons when answering the following questions. Now, there is a lot of information here, but you don't have to know a lot of this. Just note the wording here. Mean lifetime, maximum lifetime, right, up to, and this range, right? This range for the speed. Okay, so use non-relativistic physics to calculate the mean distance muons moving at 2.991 times 10 to the 8 meters per second could drop. So we're given a speed here. Don't worry about these speeds for this question, because we're given a speed, right? But we're asked to find the mean distance. So which one of these would we use? The mean lifetime, right? Very, 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 very simple. So velocity equals distance over time, and distance equals velocity times time, right? Which in this case would be 2.991 times 10 to the 8 meters per second, right? Multiplied by 2.2 times 10 to the negative 6 seconds, which is our mean lifetime, right? For mean distance. So seconds cancels out, and all we're left with is meters. And if we do the calculation, we get equals 658.02 meters, right? So 658.02 meters is the mean distance muons moving at 2.991 times 10 to the meters per second could travel, right? And we use non-relativistic physics, which is very, very straightforward here. Okay, so the next question doesn't ever state explicitly to use non-relativistic physics. which is our first clue that it is relativistic physics, right? And the second clue is the speed here, expressed as a fraction or a part of c, the speed of light, right? So when you approach the speed of light, a lot of strange things start happening, right? You probably know this already, uh, but just to demonstrate, I put a photo of the flash here. This is the muon when it starts approaching the speed of light. Now, let me show a video actually to really demonstrate this. I'll rub this out. Okay, this is what happens when a muon approaches the speed of light. Imagine that the flash is the muon here. This is what happens. Oh my! This is what happens. This is what the muon is doing. It's doing this, right? It's approaching the speed of light, and when you go this fast, a lot of strange things start happening to you, right? See, there's so much weird things start happening. Um, this doesn't happen. Okay, this I don't know what this is. Okay, this is not realistic. I actually have no clue. Yeah. Okay, we'll stop. But that doesn't happen. But what does happen is you travel forwards in time, right? So if I was a muon and I was traveling at a speed approaching c or close to c, let's say this muon was holding a clock, right? And the clock is ticking normally. Well, as this muon approaches this the speed c, the time ticking on the muon's clock would be slower than the time clicking on, say, a stationary clock relative to the muon, right? So if there's a clock stationary relative to the muon, like this, the time ticking on this clock will happen much slower than this clock. So what does that mean? Does the muon live in slow motion? No. For the muon, everything happens at normal speed. In fact, time continues on at normal speed. From the muon's perspective, everyone else's time is sped up. The muon sees this clock and wonders why it's moving so fast. Okay, from everyone else's perspective, right? The stationary perspective, we see the muon's clock is ticking very, very slow. So we're wondering, why is this clock ticking so slow? And for us, time is passing normally. For the muon, time is also passing normally, but it's wondering, why is this clock ticking so fast? So that's what happens. You basically get to travel forward in time. You age slower compared to everyone else, though time for you and around you is normal. Just everything that isn't moving with c, so or everything stationary, everything else around you, will appear to you as if it's passing by really, really fast, and as if it's in fast motion, like it was fast forwarding. So if you ever wondered why the Flash has time travel powers, although I'm pretty sure it's already sufficiently explained in the movies or something, I haven't watched the movie, so I don't know. The reason why the Flash can travel to the future, at least, maybe not the past, but in real life, the Flash could travel to the future, is because as he approaches the speed of light, his time now runs slower compared to everyone else. So as he watches everyone else, everything happens in fast motion, but for him, everything is normal. As everyone else watches him, he's moving in slow motion, right? Or maybe not moving. He's zipping by them at exactly c. So the reason why this time difference, time dilation, happens is to maintain this speed of light c. As you get closer to c, so let's say I was, uh, let's go back to the muon example. The muon is going with a speed that's 99% c, right? 0.99 c, right? If I'm saying still, okay, fine, that's 0.99 c. But let's say I'm moving this way. What do I see this muon moving as? Well, let's say I'm moving this way at 0.5 c, 50% the speed of light. Well, as I blip past this way, this muon's also blipping past this way. So I would see it if I imagine myself as stationary. I would see this, and let's say we're both in deep space, right? And I imagine myself as stationary. I don't know I'm moving, right? I would see this blip past me at a faster speed. And in this case, it'll be zero, the speed it will have will be 0.99 plus 0.5 c. Now, this is a problem, right? This equals 1.49 c. In other words, a speed that is greater than the speed of light, which cannot happen. You cannot have a speed greater than the speed of light, even if it's just a relative speed. And actually, there's no such thing as a relative speed, which I'll get to in a second. But basically, the idea is you cannot have anything greater than the speed of light. So if you start approaching the speed of light, how does the universe resolve this issue? It will literally just slow your time down. So that way, for you, time is passing over, you're moving at the speed of light. But if anyone else sees you and them watching you might make it appear to them that you're moving faster than the speed of light, then they'll see you in slow motion, right? Time will pass slower for you to prevent you from going at the speed of light. So the Flash is zipping by everyone from everyone else's perspective. He's zipping by them at either C or something very close to C. Because if he wasn't, then if they had just moved forward this way or walked in the opposite direction, they would watch him blip past as a speed greater than C. Right? So that's why time dilation happens. And that's why if you start going really, really fast, like the Flash here, you can actually time travel to the future, or at least you can go to the future quicker than everyone else. From your perspective, you've just fast forwarded to the future. From everyone else's perspective, you've been in slow motion for the past 2 years, right? Okay. So now we've got that out of the way, we can move on to the relativity question. So for relativity, you have certain equations you have to use, and they are in your formula and data sheet. In this case, we're using this equation to find time dilation. So we have to see how much the mean lifetime changes as you go at 0.99c if you're not moving, right? How much has it been changed? This is the speed that the muon thinks it's moving. And in our example before, the muon is like the Flash in our example. And we're trying to find, as observed from Earth, we're trying to find what everyone else sees. So we know that this muon's time is passing slower. It's in slow motion from the perspective of everyone else. So its lifespan will be longer from the perspective of everyone else. So we know that. And the equation we have to use to find how much longer it is, actually what exact value it is this equation. Which can also be written as this, where gamma is just equal to this. Right? This part. Okay. So what is this? What is t prime and what is t naught? I'll define that. T prime and t naught. Okay. So when we measure a time, like for in this case we have a lifespan, we're basically measuring the time between two events happening. So if we have a lifetime, we're measuring the time between the birth of the muon and the death of the muon, right? So T naught is the time that's measured by the object or person or whatever that thinks both events happened in the same place relative to them. So, relative to the muon, its birth and death happen in the same place. From the muon's perspective, time is passing normally. So, the muon thinks this is how much time has passed. Right? So, T naught for the muon, where its birth and death happen in the same location relative to itself, is equal to 2.2 times 10 to the negative 6 seconds, right? As you can see there. So T naught equals 2.2 times 10 to the negative 6 seconds. T prime is the time measured by the observer that thinks the two events that we use to measure the time, right? The time between the two events. T prime is the time measured by the observer that thinks the two events happen at different locations. So if I was standing on Earth and I watched the muon come down, it was born somewhere in space or in the upper atmosphere, and it dies somewhere much closer to the surface of Earth. Right? So I've seen its birth and death in two different places relative to me. Right? So relative to the muon, its birth and death is in the same place at the muon. Relative to me, its birth and death were in different places. First, somewhere in the upper atmosphere, and is where it's born, and then it dies somewhere much closer to the surface of Earth, right? Since it has moved relative to me. So we don't know T prime, right? That's what we're trying to find here. The mean lifetime of muons traveling at this speed as observed from Earth. So this is what we're trying to find. The observer that has seen it in two different locations is the one standing on Earth, right? The observer has seen the birth and death of the muon at two different locations, and we're trying to find how much time did he see, right? So we know the velocity that the muon is traveling at, and so we know everything. We know the velocity the muon is traveling at. We know the speed of light, obviously. We know the time measured by the muons from the muon's perspective. where the birth and death happen in the same place relative to the muon. And we don't know this, but that's what we're trying to calculate. So let's calculate it. So gamma is equal to over root 1 minus 0.997 squared, right? Which gives us 12.92, which is our gamma factor. So gamma is equal to 12.92, and t prime is equal to gamma times t naught, which is equal to 12.92 times t naught, which we know 2.2 times 10 to the negative 6 seconds, which is what we have here. So let's calculate this. That leaves us with 2.84 times 10 to the negative 5 seconds. So the muon's lifespan actually seems longer for the observer on Earth than it does to itself. The muon only thinks this much time has passed, but the observer on Earth thinks this much time has passed between the birth and death of the muon. So the observer on Earth, its time is dilated, right? His time has been dilated. He thinks the muon's lifespan has been much longer than the muon thinks its lifespan has been. And that doesn't mean it's wrong. Actually, both of these values are correct. It's just a matter of your frame of reference, right? So this is our answer. Also, just quickly note how I've not used the maximum lifespan. So the maximum lifespan is 3 times 10 to the negative 6. I've used 2.2 times 10 to the negative 6 because that's the mean lifetime, right? And the question is asking for mean lifespan. So I've used the mean lifetime, right? Okay, so what is the actual mean distance traveled by such muons through the atmosphere as observed from Earth? So as we've just seen, when you observe from Earth, this is how much time you think has passed, right? This is how long you think its life is. So if you think its life is this long when you observe from Earth, and its velocity is still the same, right? You can still have the same velocity, then the distance it's traveled is much greater, right? So we don't have to worry about relativity here because it's from the same frame of reference. So relativity comes into play when you're trying to meld two frames of references. So someone is moving, someone is not moving, or two people are moving, and they're close to the speed of light. Then you need to start worrying about, okay, well, they observe different durations of time. 1 second for one person is 2 seconds for a different person. So you have to worry about trying to meld that, and that's what this is. But here, we're worried about the same frame of reference. We know the time, the lifespan of the muons from the frame of reference of Earth. We know the velocity of the muon from the frame of reference of Earth, which is just this. Right? The velocity doesn't change. The time is changing, so the velocity doesn't have to change. Right? So the velocity doesn't change. So everyone agrees on this velocity, as long as the observers on Earth aren't moving relative to the muon, they will agree on this velocity, right? So the observers on Earth are assumed to be stationary here relative to the muon, so the velocity is the same, right? So to find the distance, we can just use the simple formula which we used up here. Which we've used up here. Distance equals velocity times time, but this time, our time is a different value. The velocity is the same. The velocity is this velocity, but our time is t prime, right? It's the dilated time. So that everything here is from the same frame of reference. Okay. So velocity is equal to 0.997 c times 0.997 c meters per second times the time, which is 2.84 times 10 to the negative 5 seconds. This cancels out, which gives us 8,494.44 meters, right? And I've multiplied c into here, right? Which c is equal to this, right? So I've multiplied c into here. So this is our answer, 8,494.44 meters, right? And let's try and make this into kilometers. So if you have something like this and you can make it into kilometers, for WACE style questions, always make it into kilometers, right? Always make it into kilometers. Right, so there we go. Okay, so just a quick lesson which I think I should touch on for all these types of questions. And I'm not sure if, because this is a very, very fundamental concept, so I'm just going to bring attention to it. All motion is relative, right? And basically what that means is you can't know how fast something is going. You can't know how fast something is going unless you compare it to something else, right? So, okay, I don't, if there's nothing in the universe except this dot, I don't know if it's moving or stationary, right? If I have another object that just appears here and that object goes like this really fast, okay, then I know that either, right? Either I'm moving like this with a certain speed v, and that's why, from my perspective, I saw this zip past me, right? Like looking outside the car window, I saw this zip past me, or I'm actually stationary, and this was the one that moved, right? With v, right, in this direction. Sorry, with v in this direction, right? But if I'm in space, how can I know which one is the truth? Well, the answer is both answers are the truth, right? So if I sit in a train, let's say I'm going in a train, and I look outside and I see all the landscape just zipping past me as I'm looking outside this train. And I tell myself, oh, well, no. The train is perfectly stationary and the entire world is actually moving back with a certain velocity. And that's what's actually happening here. Well, the other passengers in the train might look at me and say, well, no, you're actually quite stupid. Actually, you don't understand how windows work. But that's not what's happening. Actually, the guy who says that is correct. He's correct, right? You can say that. You can say that the train is completely stationary and the entire world is what's moving backwards around you, and that's actually correct. That's a correct thing to say, and the reason why is because of this: all motion is relative, right? There is no such thing as objective motion. There is nothing that says the train is what's actually moving forward. On Earth, people naturally assume the earth or the ground as a stationary frame of reference, right? If the guy in the train that thinks the train is stationary did all his math assuming the train is stationary and that everything else is moving, as long as he gets his speeds and velocities correct, all the math will work out, right? Everything will still work out. And it's because there's nothing that necessarily indicates that the Earth is stationary. If you think about it, the Earth isn't stationary. The Earth is also moving, right? If I walk forward on Earth with a certain velocity, well, the Earth is also moving with a certain velocity through space, right? So what is my velocity? Is it this velocity plus the Earth's velocity? Well, it can be, but that's not a very useful frame of reference. I'm not very concerned about the Earth's movement. So I'll just assume the Earth is stationary and I'll set that as my frame of reference, right? Assuming the Earth is stationary and that I'm moving. That's my frame of reference. So all motion is completely relative, and this becomes important later. As we saw earlier, the muon thinks its birth and death happen in the same location relative to itself. It's correct, right? To it, it happened in the same location. And that's actually a true and correct statement. There's nothing that indicates that that's a relative velocity. There is no such thing as relative velocity.